Okay. So, what we have introduced in these lectures are the discrete transformations, those go by the name charge conjugation, parity reversal and time translation or time inversion, C, P and T, and how these particular discrete transformations have a effect on the processes those are taking place in nature. So, let me say that I start with something, I denote it as C L of t, that means it is a tree level Lagrangian for photons. It is going given by 1 over f mu nu times f mu nu. And now, there is a nth order correction that is coming to this Lagrangian. I denote it by, so we have the tree level Lagrangian given by L of t plus the contribution coming from the Feynman diagram, n point Feynman diagram, which we have given as a mu 1 to a mu n and pi of mu 1 to pi of mu n, and we are trying to find out whether this particular term should actually contribute to the effective Lagrangian of the system. Now, if we are dealing with a theory that is respecting charge conjugation invariance, then this particular additional term that we have given here by L n should be symmetric under charge conjugation. So, how do we define that? It is done in the following way. So, you act charge conjugation operation on this n point Feynman diagram. So, what will happen is we have mu 1 to a of mu n to pi of mu 1 to pi of mu n into k 1 and k n. The contribution of pi 1 to pi mu 1 to pi mu n comes from the Lagrangian that is symmetric under charge conjugation. So, if we operate by C inverse from this side, then we can write here something like this, and this particular part remains invariant under charge conjugation. So, what we are left with is C L n C inverse is equal to C of a mu 1 a mu n C inverse times pi of mu 1 to mu n k 1 k 2 etc., and it stops over here. We do not pick up anything, any sign from the pi part. However, we can put or we can insert C C inverse in between C inverse C, and it continues, and you see that for every a mu with a prefix or a suffix, we pick up a factor of -1, then comes mu 1 to a mu n, pi of mu 1 to mu n, k 1 to k n, and the total sum total of this action is -1 to the power n times a of mu 1 to a of mu n times pi of mu 1 to pi of mu n function of k 1 to k n. Now, it is pretty obvious that this quantity on the right hand side will be plus or minus depending on whether n is even or odd. If n is even, then under charge conjugation L n for n point function would actually pick up a negative sign, and for n odd it will pick up a positive sign. So, what is the upshot of this particular observation? The upshot of this particular observation, that is encoded in the theory of quantum fields, is a 3-point function the way we have drawn it over here in vacuum cannot exist, because of the reason is the same. The contribution is negative of itself. So, when you add these two things together, you get a 0, and so 3-point functions in field theory in vacuum does not exist, and that is something what is known as Furry's theorem. The same thing would be true if the momentum content of this external attached line tends to 0, that is k tends to 0. That means, we are actually talking of these two diagrams together, and effectively as k tends to 0, the momentum assignments does not undergo any change, and you can actually think of having a 2-point function for all practical purposes. And as we have discussed already, that the theorem statement does not depend on the momentum of the particles in the loop or of the external lines, it is 0 in vacuum. However, because this particular insertion actually introduces a additional factor of E times magnetic field and or electric field, and the effect of E b is basically introduces a odd number of photon vertices. So, because there are odd number of photon vertices, those are introduced here, the effect of this particular correction to the theory is nil. So, the question that arises here is, does it happen always for all diagrams those contribute to the effective Lagrangians with powers of magnetic field, those are even or odd? It turns out that for systems in vacuum, if the power of the magnetic field happens to be even, then there is no problem. The reason is, as I have already mentioned, the n actually becomes even, total number of vertices, electromagnetic vertices becomes even. So, minus 1 to the power any even number is 1. So, here we survive. but if B is odd, we do not. So, that is the end of the stories as far as vacuum field theory is concerned. Thank you.